Hello, everyone. Welcome back to CPE 517-WS Digital and Computer System Architecture. This is part 3, limitations of instruction level parallelism. So what limits the instruction level parallelism, right? So, and what's the real ceiling of instruction level parallelism? What's the best you can achieve with instruction level parallelism for all the benchmarks we're trying to do? This is the topic of this part, right? We're gonna use, we're gonna do some conflicting studies on some benchmarks by changing the hardware and software sophistications. So we want to say how much instruction level parallelism is available by increasing the hardware budget. Do we need to invent new hardware and software mechanisms to keep on the processor performance curve? There are quite a bit of them, right? So to study this, our assumption is we have the ideal machine to start with. Like for register renaming, we have infinite virtual registers. For branch prediction, we have perfect branch prediction. For jump prediction, all jumps perfectly predicted. Memory address aliasing, that's what we talked about before. Like A plus 20 equals B plus 10. So you can see A and B are aliasing memories. So from their name, you cannot see they're similar, but when they add some different numbers, they become the same. We assume we have perfect memory aliasing analysis, right? 2 and 3, no control dependency, perfect speculation, an unbounded buffer of instruction available. Okay, so for this model, we have everything perfect or infinite, right? We compare it against the Power 5, which is a very popular CPU at that moment. As you can see, here the instruction window size means the set of instructions which can be executed out of order in a speculative processor. Okay, as you can see, for the perfect, everything perfect, which is definitely not possible, but for the perfect case, we can achieve like 54.8 GCC instructions per clock cycle, 62.6 espresso, which is a quantum simulation, quantum application, instructions per cycle. Li is a solver. FPPP is a Fortran some program, and then Duduce is another program. Tomcat is a server, like HTTP server. So you can see for this kind of perfect machine, we can achieve 150.1 instructions per cycle. Well, actually, we cannot be perfect, right? We cannot allow infinite amount of instructions to be executed out of order. Assuming we have a realistic case like a 2K, half a K, 128, and 32. We see the instructions per clock cycle reduces from 52 to 36, then to 10, and then to 8. So for the espresso, it also reduces from 63 to 8. For Tomcat, it reduces from 150 to 14. So it's like 10 times, around 10 times reduction, right? From infinite to like a 32 window size of instruction. Okay. Well, we should also be aware that we cannot allow then let's say we'll assume we have the best, like 2K, which is a huge. It's the best of the heuristics we had here. We have like 2K, 512, 128, 32. So we choose 2K as the real case, which is the upper bound, the best case of the configurations. Instruction issued per block clock is 64. On branch prediction, we definitely cannot assume we have the best. We have to say, okay, then we have some tournament or 2-bit or profiling versus none. We can see that for the predictors, it further reduces the selective predictor is like correlated, right? So we can see the correlated reduces from 30 to 5.2 instructions per clock cycle to 8, 12, 16, 48, 15.1, 45.5. So it reduces a lot of the performance, right? And then the misprediction rate also have like around at least 5%, 6%. Sorry, the selective is tournament. It's called in this case tournament. That's why it's selecting from either global or local predictor. Okay. Then with that, we can see the misprediction rate is either around 1% or up to 16% is the 2-bit counter, right? So if it's tournament, it's like 3%, 2%, 2%, 4%, 6%. It's like that. So we have some misprediction rate. Register renaming, we definitely cannot have infinite amount of number of registers. So we have to assume some realistic cases, like we have 256, 128, 64, 32. By doing that, we further reduce the performance to like from 10.7 to 10.4 and then down to 4.3. Similarly for all of them, it's turning down, right? And then for memory aliasing, assuming we have perfect versus stack versus inspect versus none, this gives a lot of dependencies because you don't know what's the dependency. A lot of times you have to wait until the memory flashing to be finished. So it reduces from 10 cycle, 20 instructions per cycle to 7 to 4. Similarly for all other things. So taking them together, you can see that probably inspection is the case. So what you can get is with very good machines, we have only like 4, 5, 6 instructions per cycle. That's the best we can get. Okay, so this tells us one thing, that is instruction level parallelism has a lot of limitations, right? No matter how many hardware resources you put in, it's very likely that you eventually didn't get any benefits, right? So, okay, but before we move on to discuss a little bit about this, let's talk some things we discussed about how to improve the instruction level parallelism by using either hardware and software. In hardware, we typically, when it goes to hardware, typically what we want is for runtime adjustment, right? Like memory disambiguation, we have to do it in runtime is the best because typically even the code is different, but the address would be the same. Speculative, hardware is the best. Exceptions are easier for hardware to handle and does not have to bookkeeping the code or composition code. It's very complicated to get it right. For scheduling, software could look ahead for scheduling better. Compiler independence does not require new compilers recombination to run well. So as you can see, for runtime, something that you cannot decide proactively, it's typically better for hardware, right? But for the things that you want to know the insights or you need a global view, it's typically better you do hardware software perspective. So then we go to another thing is concluded here. We can see for the performance with very good machines, right? With how many? With this good machine, right? 64 instruction issued per clock, instruction window size of 2048, register renaming have as many as 256 integer and 256 floating point registers. Branch prediction is 8K 2-bit predictor. Perfect cache, perfect cache, right? And then memory aliasing if we have inspection based. So for that, we still see the performance, that's very good machine already. So for that, the instructions per cycle is only like 6, 4, 5 instructions per cycle, right? In that sense, we see there could be some applications that has a lot of parallelism, such as database or scientific code like matrix multiplication. And then we can then take advantage of that by using explicit thread level parallelism and data level parallelism, right? Thread proceeds with its own instructions and data. Thread might be a process part of a parallel program of multiple processes, or it might be an independent program. Each thread has all the states necessary to allow it to execute, like instructions, data, PC, register, and so on. Typically, there's no communications between threads, like dependencies. For data level parallelism, it's basically will perform identical operations on all the data in parallel, such as single instruction, multiple data, right? So for this kind of cases, what do we want to say? Let me show you some example, right? So for instance, if we want to do grayscale of an image, okay? What do we mean by explicit parallelism, right? So assuming we want to do grayscale, we can actually assign 9 threads to these 9 pixels. All of them can add the RGB together and average them out. So that is the grayscale, right? So we can see you can also write it in another way that in a for loop, every iteration you finish with 1 pixel and next pixel, probably some sort of parallelism. This kind of parallelism are independent. You can easily actually extract it by human involvement, right? So if the programmer explicitly tell you that all these pixels can be executed in parallel without any dependency, that would be significantly easier than you use the hardware and the software of the instruction level parallelism to extract the performance gain. Why? Because the programmers actually tells you what is the hints. It's like I give you a hint saying, okay, this is the hint. Can you take advantage of the hint to make it better, right? This is observed in a lot of applications. This is image processing. It can also be in machine learning or matrix multiplication, right? So I'm trying to give you a lot of examples why we do that. The reason is that we want to tell you that this is very popular. Right? It's not a rare case, like we just got a corner case and then keep saying, oh, this is popular, this is very good, so we want to make it better. Actually, it's a lot of applications are the same. They show explicit parallelism that can be easily hinted by the programmer to the computer. For instance, the matrix operations like matrix multiplication. Okay, it's A, B. If A and B multiply together, and we get a C. So what we can see here is like this, right? For all of you guys, I believe you must learn that this row multiply this column gets these elements, right? And then the first row multiply the second element column, probably get the second elements. So basically for this row of I, J, you easily know that we can finish this by row I and column J, row I of A and column J of B to multiplication, right? So you can see this A and B, they can read them in parallel, and the computation of every entry of the destination result matrix, like this is result matrix. It's also sort of in parallel, right? Can be done in parallel. So in that sense, we can just tell the computer this can be a data parallel, like application. Like for all the entries, they do the same, like one row multiply one column, right? So this is data parallel. So then there's no dependency to resolve from any threads or any instructions. It's just the same for all of them. Well, this is, we talk about image, we talk about matrix, or matrix multiplication can be used for scientific application, like high performance computing, linear algebra, like some solvers, LU factorization, if you learn about linear algebra, or solve AX equal B. Matrix multiplication can also be used for graph computing, graph analytics, network analysis, or machine learning training. And also in scientific data, like Tomcat, you see that HTTP application, right? In that case, we can also actually allow different threads to be responsible for different requests. Taking that into your mind, you can see that there are a lot of applications, they come naturally with parallelism, right? So that's why we want to explicitly tell the computer there exists parallelism. How to do that? That's what we're going to talk about in thread level parallelism and data level parallelism, or OpenMP, MPI programming, right? So you explicitly tell each thread, what are you going to do? Okay, then the thing comes to a very important problem. If that's the case, why people still come in loves instruction level parallelism? Like, what's the benefits? What are the benefits of instruction level parallelism? Why instruction level parallelism is so fascinated? Everybody wants to go after it. Then, if that's the case, so after we discussed in prior changes of different configurations, right? So hardware is one thing. So can you tell us what could be the problem that prevents us from getting a better performance from instruction level parallelism? Is that dependency? Can the computers resolve it by themselves automatically? So combining this idea with these motivations we discussed, please give us a 15 to 20 minutes discussion about these two questions, okay? That's it for this part.